Hi friends, today we discuss some more properties, mainly the linear property of the Laplace transform and shifting property of Laplace transform. But before that, we establish a very important formula, Laplace transform of t to the power n. So what is the Laplace transform of t to the power n? So the formula is given by Laplace transform of t to the power n is given by factorial n by s to the power 1 plus n. So how can I prove? So start in this way. Suppose Laplace transform t to the power n can be written as 0 to infinity e to the power minus t into t to the power n dt. This is our Laplace transform. So we multiply by e to the power minus t and taking the integration 0 to infinity. Now we substitute. So we substitute st equal to u. So if we take st equal to u, then what is the value of t? T can be written as t equal to u by s. Now differentiate dt equal to du by s. Now we change the limit. So if t equal to infinity, if this t equal to infinity, then s into infinity will be infinity. So limit of u will be infinity. And if t equal to 0, then s into 0 is 0. So therefore the limit of u is 0. So therefore limit becomes 0 to infinity e to the power minus u, and the value of t we put u by s to the power n, and here dt we replace dt by du by s from this formula. Now what we get? So we have here s to the power n, and here we have s. So this term will comes out. So this becomes 1 by s to the power n plus 1 integration 0 to infinity e to the power minus u into u to the power n du. Now remember that this is a gamma function. So this value is given by gamma of n plus 1. So we get gamma n plus 1 plus s to the power n plus 1. So this is the Laplace transform t to the power n. So Laplace transform t to the power n is given by gamma n plus 1 s to the power n plus 1. In particular, if n is an integer, then gamma n plus 1 is given by n factorial. So Laplace transform t to the power n becomes n factorial by s to the power n plus 1, where n is an integer. So this is a very important and formula we use many times. Next, some important properties of the Laplace transform. We start with linearity property. So what is linearity property? If C1, C2 are any constant and F1, F2 are function with Laplace transform F1s and F2s respectively, then Laplace transform of C1 F1 plus C2 F2 is given by C1 L of F1t plus C2 L of F2t. That is C1 of F1s plus C2 of F2s. So this property known as the linear property. So proof is very easy. So Laplace transform C1 F1t plus C2 F2t, we how should we write? 0 to infinity, we take e to the power minus st, and then we put this value here. Now this is simple integration. So C1 is a constant. We break this like this equation, and you have this is the Laplace transform of F1s, and this is the Laplace transform of F2s. So you get C1 F1s plus C2 F. So this is a simple formula, uh, proof of the formula. Now we apply in the following. Take an example. Laplace transform 4t square minus 3 cos 2t plus 5 e to the power minus t. So we can break like by the previous formula, the linear property, we can write 4 into Laplace transform t square minus 3 into Laplace transform of cos 2t plus 5 into Laplace transform e to the power minus t. Now we know what is the Laplace transform t square. Laplace transform t square by factorial 2 by s cube. And what is the Laplace transform cos 2t? We proved in the previous lecture that Laplace transform cos t becomes s by s square plus 4. And similarly, for e to the minus t, we get 1 by s plus 1. So just simplifying, we get this. So here is the exercise. You can note it down and try to solve. I also give you the answer. You guys can try and check this one. Next we prove first translation or shifting property. So what is shifting property? So let Laplace transform of ft is given by fs, then Laplace transform of e to the power at ft is equal to f of s minus a. So look here, if you have a Laplace transform taking a by multiple, here you have a the function has a multiplier e to the power at, then this fs is shifted to f of s minus a. So if you take a multiple by positive a, then it is mm, shifted by negative a of a. So again, this is a simple proof. So try to find from the definition. So we write e to the Laplace transform e to the power atft, that is 0 to infinity e to the power minus st, and put e to the power atft. Now we write it together. So these terms will add up, and we, if these two terms are add up, we get e to the power minus s minus at. So here you have s minus a. So suppose s minus a equal to e, then it become e to the minus ut ft dt. So you have this is f of u, that is f of s minus a. So again, this is a very simple proof, but this is very useful. We use in many problems this property. So you have to remember this property. This is a very useful property. Now try to find some example. Evaluate Laplace transform t square e to the power 3t. So we know that. So your function is here t square, and you can assume that it is multiplied by e to the power 3t. So since it is some function is multiplied by e to the power 3t, then you can use the shifting property. So first find what is L of t square. So L of t square is given by 2 factorial by s cube. So I assume that this is equal to fs. Now L of t square e to the power 3t, here it should be positive 3 positive. Then it is shifted by minus a. So if you have a positive, so there is a just a little mistake. This should be positive. Then f of s minus 3. So by the shifting property, here you have the shifting property f of s minus 3. So you have e to the power 3t. So this will be shifting by f of s minus 3. So what is f of s? This is your f of s. So what is f of s minus 3? 2 by s minus 3. You just replace s by s minus 3. So 2 by s minus 3 whole. There are few more exercises. You just pause this exercise and try to solve. I also give the answers. So this will be some easy exercises for you. Now some application of the first 15 property. Again, these are very simple application. So what will be L of e to the power at t to the power n? So this will be shifted by a e to the power at. This is multiplying at t to the power n. So what is the formula of t to the power n? N by s to the power n plus 1, and it will be shifted by a. So this becomes a s minus a whole to the power n plus 1. Similarly, what is the Laplace transform e to the power at sine bt? So it will be, for if it is simple sine bt, we have b by a square plus b square. So now here multiplied by e to the power at. So this is just shifted by s is shifted by s minus a. Similar for cos sine hyperbolic and cos hyperbolic, similar formula. Now try to solve some example. Evaluate Laplace transform e to the power 2t cos square t. So first we try to find what is the Laplace transform for cos square t. So Laplace transform cos square t. So we can write cos square as half into 2 cos square t. We just divide by divide and multiply by 2. So now use the for half will be comes out by the linearity property. This half will be comes out. So here we write half, and this 2 cos square t. So what is the Laplace transform to cos square t? Cos square t can be written as 1 plus cos 2t. Now you can use again the linearity property. So using linearity property, I can write a half L1 plus half of L of cos 2t, Laplace transform of 1 and Laplace transform cos 2t. So what is the Laplace transform of 1? So the Laplace transform of 1 is 1 by s, and cos 2t is s by s square first. So you just simplify and get this result. Now is the shifting formula. So this is function is multiplied e to the power 2t. So your s will be replaced by s minus 2. So you just replace s by s minus 2 here and you get this result. Another example, suppose Laplace transform Laplace transform e to the power 3t root t. So we'll try to find what is Laplace transform root t. So Laplace transform root t can be written t to the power half. And t to the power half formula is gamma 3 by 2 s to the power 3 by 2. So that can be written as half gamma half. So we are using the function, using the property of gamma function. Gamma n plus n is given by n gamma n. So using that property and gamma half, we also use the result that gamma of half is equal to root pi. So using this result, you just put the value, and here it is shifted by e to the power 3t, so s will be shifted by s minus 3, and you will get this result. It is simple calculation. Now another, maybe we can consider as a theorem. If Laplace transform of ft is given by fs, then Laplace transform of sine hyperbolic at ft is given by half f of s minus a minus f of s plus a. So this proof is again simple. We write this Laplace transform sine hyperbolic t ft. Now put the value of sine hyperbolic at. What is the value of sine hyperbolic at? It is half of e to the power at minus e to the power at into ft. Now you just break in the linearity property. Use the linearity property and break these values. And again that it is shifted by e to the power at is multiple. So here it will be shifted by a. So this is s minus a, and it is here it is a minus a. It is shifted by minus a. So we are getting f of s plus a by shifting property. And application of this above problem. So suppose evaluate Laplace transform sine hyperbolic 2t sine 3t. So this is sine hyperbolic 2t and sine 3t. So what is the Laplace transform sine 3t? So Laplace transform sine 3t, use the formula that Laplace transform sine hyperbolic 3t is 3 by s square plus 3 square. We have written down here, and it is multiple by sine hyperbolic 2t. Whenever you are multiplying by sine hyperbolic 2t or some at, you are getting that is shifted by e. So here your first your, this s is shifted by s minus 2, and second case s plus 2. So you just simplify and you get this result. Now similar result, you can prove that Laplace transform cos hyperbolic at ft equal to half of f of s minus a plus f of s plus a. So previous example, for the sine case we have a minus in between, and for the cos hyperbolic case we have the plus in between. Again, this is a similar proof, and I leave it as an exercise. And you can also find this exercise again, so you can try to find and see. Now again, a very important example. The Laplace transform of t sine at is given by 2as by a square plus a square, and Laplace transform of t cos at is given by a square minus a square by a square plus a square whole square. So here also there will be whole square. So their formula will be there is a whole square. So here we use the Euler's formula. So first we know that Laplace transform of t is given by 1 by s square. So this we already know. Now e to the power I at is given by cos of at plus I sin at. This is Euler's formula. All know that. This is famous Euler's formula. Now try to find Laplace transform of t e to the power it. So here you can use the shifting formula. So here what is the coefficient of t in the power of e? So ia. So this is shift s will be shifted by s minus ia. So we just write this formula s minus ia whole square. Now we rationalize this value by multiplying s plus ia whole square numerator and the denominator. Now simplifying this, we get a square minus a square plus I into 2as by a square plus a square. Now we all know by the Euler's formula, Laplace transform of t to the power it equal to t into cos at plus I sin at, and we break this also in the, this is the real part and this is the imaginary part. We break this value. Now we use the, again, the linearity property. Using linearity property, you can break it this like Laplace transform t cos at plus I Laplace transform t sin at. So here this is the real part, this is the imaginary part, and here this is the real part and this is the imaginary part. So we can compare the real part both sides. We can comparing real part both sides. We get this is the real part. So Laplace transform of t cos t is equal to a square minus a square by a square plus a square. And comparing the imaginary part, we are getting Laplace transform of t cos sin a t equal to 2as by a square plus a square. So next day we will see some more examples and more properties and their examples.